Welcome back to AUTS. In this video, we'll be going over Atwood machines and what they really are, how they work, how the acceleration within them works, how it connects to Newton's second law, as well as how to solve problems regarding Atwood machines. Okay. So an Atwood machine looks similar to this, okay? One pulley and two masses on either side. The rope is strung over the pulley and connects to one mass and then another mass as well. So when one mass falls downward with acceleration A, the other mass goes upward with acceleration A. So the acceleration is constant throughout this machine, okay? If these blocks won't have different accelerations. They'll have the same one, but in different directions. The string has the same tension magnitude throughout, which means the tension over here is going to be equal to the tension over here. So if I was to draw the free body diagram for M2, right? We know mg is pulling me down, force of gravity. And what's keeping me up? Tension. But when the mass is released, mg might be greater than tension, which leads to a net force, and I start falling. Because net force means acceleration, right? And for M1, so this is M2, M1, same thing, mg downward, tension upward. And both these tensions are going to be equal. They're not going to be equal to mg, they're going to be equal to each other, right? Because the tension across the rope is the same. When you pull on a rope from one side, the rope feels that same tension from the other side. So we're going to have the same tension here, okay? Same acceleration and same tension magnitude here. And you're going to have one free body diagram per mass. So, for example, right? If I had my Atwood machine here, I had M2 and I had M1. Then when I release from the system, I'm going to write an equation for this one, for this free body diagram, because you remember how in the vector video, vectors pulling forces, we learned how to write equations for each component of a force and how to cancel those out and how to find the total force like that. We're going to do something similar here, okay? For M2, it's going to be net force is equal to what? What's pulling it down? mg, right? And if we consider M2 to be the larger mass, okay? If M2 is a larger mass, this only works when M2 is a larger mass, because that's when it's going to pull it down, right? So M2 is greater than M1. Let me establish that beforehand. Then tension minus mg. So what I'm going to do is I'm going to consider that the positive direction, up is the positive direction, okay? And down is negative. So that's how I got this. And for the other free body diagram, it's going to be similar, right? Net force is equal to, so here's going to be m2g. Let me just write that here. Forgot to write that. Same tension magnitude minus m1g. Okay? But the thing is, you don't know whether you're going to consider, what acceleration are you going to consider negative and positive. If it's going downward, I'm going to consider it to have a negative acceleration, okay? Which means if it's going upward, which is block M1, that's going to have a positive acceleration. So if I replace net force with MA here, both these net forces, I'm going to replace them with MA, because net force is equal to MA, right? But they're not going to have the same acceleration. MA here, right? This block is falling, so it's going to be a negative acceleration. This block is rising with the same acceleration magnitude, but since it's rising, it's in the positive direction, so I'm going to keep it that way. Okay? So then, I can divide the negative on both sides. So divided by -1. And this equation will be revamped to the tension turns negative and m2g turns positive. Okay? So that makes sense. right? And over here, I'm going to put m2a. Over here, I'm going to put m1a. So since it's falling, right, it's going to have a negative acceleration, which makes sense. Now, how am I going to find either the masses of the, how am I going to find the masses or the acceleration here? Because acceleration is the same, right? How can I find that acceleration? Well, I could just substitute in acceleration for something else and then find that, right? But there's also another way to do it. I could add both the equations. And you see what happens here, right? Tension cancels. Because tension is constant throughout, right? The net force of the total system, the tension on one side is going to cancel out with the tension on the other side because they're acting on different objects and they're equal in magnitude. And the rope has constant tension throughout, right? It's going to become m1a plus m2a is equal to m2g minus m1g. Okay, which makes sense. Then over here, what am I going to do? I want to isolate acceleration, right? Acceleration times m1 plus m2 is equal to m2g minus m1g. So we can factor the g out here as well. A is equal to g times m2 minus m1 over m1 plus m2. There you have it. Right, now, so if I look back here, is there a way I can substitute this A into this equation to find out tension itself? So let me erase this mess here. Okay. And then this is going to be tension. So let me go back to green here. In this, I could use this equation, right? Tension is equal to m1 times g plus A. So tension is equal to m1 times g plus g times m2 minus m1 over m1 plus m2, right? Because that's what acceleration is. I can substitute this in for that. Tension is equal to m1 times, so this I can multiply by m1 plus m2. I can multiply g by that. So I'm going to get g times m1 plus m2 plus g times m2 minus m1 over m1 plus m2. And then tension is equal to m1. So g m2 and gm2 add together to become 2gm2. But over here, the m1, gm1 and negative gm1 cancel out over m1 plus m2. So tension is just equal to, if you multiply this m1 out, it's going to be m1 times that. So pretty straightforward, right? And these two equations might look a tad bit different if you used, tension equation won't look different, but acceleration might look different if you used falling as positive and rising as negative, okay? But either way, same equations. Now let's look over an example on how to do problems like these. So there's two masses over one pulley, okay? So M is equal to 12 kg falls, M is equal to 8 kg rises. That's pretty intuitive. So now let's find out how to solve for the acceleration here, okay? Acceleration and then tension as well. So for the 12 kg block, if I draw my free body diagram, mg pulling me down, and then tension pulling me up, right? So ma, or just net force here, net force is equal to tension minus mg, okay? That's going to be ma is equal to t minus mg, and since a is negative because it's falling, it's going to be negative ma. So it's going to become ma is equal to mg minus t. I can divide both sides with a negative. Let me represent this as m2 here. So M2 is going to be, we know what that is, right? 12 kgs. 12 kg times acceleration is equal to 12 kg times 9.8 minus t. So 12 kg times 9.8 is around 117.6 newtons minus t is equal to 12 kg times acceleration. Okay, so we have one of our equations. Now if I was to do the other equation, which would be for the 8 kg, I'd count its acceleration as positive, right? Because it's going upward. 8 kg times A is equal to, same tension would be positive here as well, and minus mg. So this would become mg over here, could substitute in for t minus 8 times 9.81, and that's going to be newtons. So 8 times 9.81, or I could just do 9.8, 78.4. So t minus 78.4 newtons is equal to 8 kg times acceleration. So yeah, that's our final two equations, right? And then we could add both equations to get 20 kgs times acceleration is equal to, the positive t and negative t cancel out, 117.6 newtons plus minus 78.4 newtons, so 39.2 newtons, and acceleration is equal to that divided by 20, so 1.96 meter per second squared. Pretty straightforward, right? And then if I wanted to solve for t, I could just substitute this value into either one, right? So if I wanted to go for, let's look at this one. Remember the equation for this one was 12 kg times acceleration is equal to t minus the 12 times 9.81, right? So that was, let me pull it back up, 117.6 newtons. And since we define acceleration for this as negative, this would have been 12 kg A is equal to 117.6 minus t, right? Because acceleration here is falling, but I want to keep the same magnitude. So acceleration, we can substitute in 1.96, 12 times 1.96, okay, minus 117.6 divided by negative 1. So that should give us 12 times 1.96 minus 117.6 divided by negative 1, 4.08 newtons. Okay, and that's how you solve an Atwood machine. Okay, so let's go over some practice first. And obviously these are the more basic ones. The more complex ones will be on autolearning.com and the PDF I push out later. Okay, a 15 kg mass and a 9 kg mass hang over an Atwood machine. Alright, find the acceleration and the tension in the string. So as always, make two equations here. 15 kg times acceleration, ma, right? For net force is equal to ma. Net force is equal to what? Tension minus mg. So net force, I just substituted it with ma. So 15 kg times acceleration. And if I want to consider the downward direction, and the negative direction, it's going to be negative 15 kg times acceleration is equal to t minus m is just 15 times 9.8. Okay, which is should give me around Negative 15 times 9.8. So this should be negative 15 kg times acceleration is equal to tension minus 147. And then for the 9 kg block, acceleration would be positive. So 9 kg times acceleration is equal to, same thing, positive tension because tension is in the positive direction, minus mg in the negative direction. Okay, so this should give me 9 times 9.8. 9 kg times acceleration is equal to tension minus 88.2. And then if we're going to add these two equations, we're going to get, since the tension here, we could divide the negative here, right? So, to make it a bit easier, we could divide the negative 1 out here and turn this entire expression negative. So we can multiply this thing by negative 1 and make it into 147 minus tension. When we add these equations, the tension cancels out. 15 kg A plus 9 kg A is 24 kg times A. It's equal to 147 minus 88.2, right? It's 58.8. And acceleration is equal to this divided by 24. So 2.45 meter per second squared. And the tension in the string, you could just substitute this value in for any of them, right? So if I look back at this equation here, instead of acceleration, I could just plug in 9 kg times 2.45. Whoops. And then to isolate tension, I could add this on both sides, plus 9 times 9.8. That should give me 88.2 plus 9 times 2.45. Or 110.25 newtons. And that acceleration is just 2.45 meter per second squared. Okay, pretty neat. And if you look at this problem, which is very similar, 70 kgs and 65 kgs. So 70 kg times acceleration. So they're, first let me read the problem, right? They're buckets. So buckets over a pulley on top of a building. If you want to find the acceleration and the rope tension, we're going to have to use the same strategy here. So 70 kgs and 65 kgs. 70 kg times A is equal to tension minus 70 kgs times G, or 9.8. And then since we know acceleration is downward, I'm just going to give this a negative. So if we divide by the negative on both sides, this will be, what is this 70 times 9.8? 686, right? And this is going to become positive because when I divide by the negative, this is going to become a positive. Minus the tension here. Okay, so this is one of my big equations. What is my other equation? The 65 one. So 65 kg times A is equal to, the tension is same thing, positive, right? And this time that acceleration is also in the positive direction. So I'm going to keep it that way. Minus mg, or 65 times 9.8, which is 637. If I add these two equations, right? So let me pull a full equation here so you can see what my steps are. The negative t and t cancel. I said 70 plus 65 becomes 135, right? 135 kGa is equal to 686 minus 637. And this would be in newtons. So A is equal to, what is 686 minus 637? That's 49, right? 49 newtons over 135 kgs. So that's equal to 0.36 meter per second squared, which makes sense, right? If the blocks were more evenly matched, they would accelerate less because they'd be more balanced. So if you know that acceleration is equal to that, then I could just remove this equation. And even this one. And I could just substitute in this acceleration here. So 70 times 0.36, whole thing in newtons, is minus 86. And then if you divide that by -1, you can get your tension. So it's 70 times 0.36 minus 686 divided by -1. So your tension should be 660.8 newtons. Okay? So that's pretty neat. And this one you can try by yourself. It's a bit more of an extra. It just explains why A is equal to M2 minus M1G over M1 plus M2 gives A is equal to 0 when M1 is equal to M2. Connected back to Newton's first law from session 1. So something along the lines of the objects at rest, they'll stay at rest. And if they both have the same mass, they're not really going to move, right? They're going to stay at rest. Equilibrium. Or constant velocity as well. That's also still no net force, right? In next video, we'll be going over blocks and hanging masses or ramps and inclines. So watch out for that because those are the more harder. And Atwood machines are a tad bit more